Second part of our tutorial on the mechanical wrench. As we remember, we had the geometry defined, and then we were able to control some of the boundary conditions of the mechanical wrench. We in fact introduced one boundary condition, and that is, if you look here, the boundary condition on this surface of the bolt, and we introduced this as a fixed displacement boundary condition. So what we want to do is actually make sure that we have applied the fixed displacement boundary condition, and then we wanted to put a force on the wrench of a magnitude that we defined already in the parameters as 150 newtons downward. So let's go back and look in the model builder panel. And under solid mechanics, then we have already now selected linear elastic material, and then all boundaries are free except those that are overridden by our actions. And in fact, we did override only one boundary, which is boundary number 35, which is right now here, as you can see. So we'll bring it into this position. So we can see that this boundary is actually the one that has fixed displacement, meaning that it's going nowhere. So it's neither in the x direction or y or the z direction. So let's bring it back to the standard view. And then what we want to do is apply another boundary condition here, and that is a mechanical force. The mechanical force will be acting on the wrench, and we have the magnitude, and the magnitude is defined in the global definitions where we define the parameters in there. So in the global definitions, then we have to define parameters, and the parameters we introduce here, the name is f, for example, and the expression for it is 150. And don't remember that we have to put in the units in square brackets as MPa, which is megapascal, and it does write it for us as 1.5 times 10 to the power 8 Pascal. And then we can put a description that helps us to remember, like applied force, for example. In addition, we can add in the future any other parameters that we will use in this model. For example, in this lecture, what we will do at the tutorial, we will also practice controlling the mesh size and determine the effects of the mesh size on the results. As we will see, if we have a very coarse mesh, then the results will be crude and sometimes too exaggerated. So we have to get a very fine mesh, and having a fine mesh everywhere is very time consuming, because we can get a very large size model that requires a lot of time. So I'm going to talk a little bit about controlling the mesh and how we will be able to control it even parametrically and do the study parametrically. So I'm going to put here two parameters. One of them is a divider value that will be used to take an initial value of the mesh size, the average mesh size, and then divide it smaller and smaller and smaller. So initially this divider parameter is 1, and then we're going to describe it as divider parameter. And what is it going to divide? Is going to divide the average mesh size. So the mesh average is it's basically we have pyramids, three-dimensional pyramids. So they have some height, width, and they have an average size. So this average size, we're gonna put it as H0. So H0 is an internal variable that COMSOL knows it is the initial value or the value of the mesh, size. So I'm going to put it here as let's say we have here 1 millimeter. So if you look at the dimensions of the wrench here, you get 50 millimeter from this point to this point is 100 millimeter. So if you want approximately like 100 elements across, we can put like 1, but then we have to write what is the units. So the units, we're going to put millimeter here, and this will be initial mesh size. So these are kind of values that we will use later on in our parametric studies. So we've now defined the global definitions in the parameters. We can contract the node to get it out of our way. And then we have, we check the materials node. We have already selected steel. So these are the steel properties. And note here that the ones that are checked in green are the ones that are actually going to be used in this model. These are the ones that are used in the physics. All of the other ones are not going to be used. However, they are available in case we add an additional physics that would require these properties. In case the additional physics requires more properties, then we have to actually do the modification ourselves and put in additional properties in this material database. So now we go to the solid mechanics, which is the physics node. And the physics node, we first defined it as for the 2 domains. So we're solving solid mechanics for the wrench, solid mechanics for the bolt. And it is described as linear elastic material. So there's no plasticity, there's no creep, there's no other nonlinearities in the material. And all of the boundaries now, we're starting to look at them as free. That comes as a default with the D. And we don't have to worry about initial values because we have a steady state or a stationary solution. It doesn't require initial values at all. So we put in a fixed constraint on this boundary here, which is the bolt. Now we move on to the last boundary, which is let's try to see if we can bring it to a position where we can see it better. So we want to put a force on that on this boundary. So what we do is we go into solid mechanics and then right click, and the right click is going to show us a number of boundary conditions. All of these are boundary conditions. You can see that there's a little icon here that shows a boundary so that you can see that these are boundary conditions. You put them on a surface, and later on we can have pairs. For example, if you have a bolt contacting with the wrench, this is a pair, and you can have a contact. You can additionally prescribe what's happening in between them. If you have like some kind of rubbing or pulling or whatever, then we can model that as well. You can also define boundaries on edges or on points. So for here, we want to add a load, and therefore you can see if you go down, free, boundary load, fixed constraint, prescribed displacement, prescribed velocity, and so on. So what we want is a boundary load. So it adds a boundary load, and then we need to see what is it, how much it is, and we also apply it. So we can see that if we want to apply it where, we're going to click, left click, it will highlight it in red, right click, it will select it as boundary number 111. Okay. Now what do you have on it? What we have is the type of load. We can have 2 types of loads. One load is pressure. We can put a pressure, which is a load per unit area, or we can put a total force on that boundary. So if you look here, you can see either total force or the pressure, or a user defined as force per unit area. So what we want is the total force, because we know the total force is 150 newtons, and it will distribute itself on that boundary. So the total force here, then it tells us what are the total force. The force is a vector. It has x, y, z, and we know that it is going to be in the z direction and it's downward, so it's going to be down minus in the minus direction. So we skip the x, skip the y, and we put the component in the z direction, which is minus, and now we can write minus f, because it will substitute 150 that we put in the global definitions. It will substitute it here for f, and therefore we have done our job in specifying the boundary condition. So let's go now to the study. We finished now the physics, then we go to the study. Now we have already defined the study, if you look at the study node, as a stationary study. So the stationary study is not time dependent, and we can actually compute things right now because there are some default values that can be used in the mesh. So let's see what we can do here. First is to explore the mesh idea a little bit, and then we go to the study, because all what we have to do is right-click and right-click on the study, and then we can compute. So let's go to the mesh and then see what's in the mesh. At this point, it says physics control mesh, which is the default value, and the element size is normal. So in order for us to see what the mesh looks like, which is what COMSOL suggests here based on the physics, we can build it. We click on build all, then it will take a little time to process, and you can see in the messages below here it says that it has 2 domains and then 197 boundaries and 450 edges and 264 vertices, and it did already produce this mesh. So the mesh, if you look at it here, you'll see that it is you just have you can play with it, and then you can see it is across the thickness of that wrench. We have only 2 layers. It's 2 meshes, like 2 elements thick across the layer. That might not be sufficient, and therefore we may need to do something a little bit finer. Although if you run it, if you look at here the number of elements, that's 125,000 elements, and that's kind of reasonable because the degrees of freedom are roughly like 3 times the number of elements, or could be more in this case for solid mechanics. So it's not very excessive. It gave me a couple of warnings because the mesh is too coarse, that it cannot make resolution sufficient for some of the curvatures here. Then I can go back and actually change that to say a user-defined mesh. So I can do the mesh by myself. And then the mesh, I can do it by myself by looking at user-defined mesh. Then it gives me an option either to have the size of the mesh and what do I do with the free tetrahedra. So let's look at the size. The size of the mesh, it says predefined as normal. Then I can do it custom, for example. And the custom, it gives me minimum element size and the maximum size. And then, for example, this is 0.01 meter, 0.013, so I can make it even smaller, the maximum, or 5, for example, and the minimum, I can have it maybe half of this, 0.001, for example, or 0.02, and then it grows the mesh between the minimum and the maximum at a certain rate, like exponential rate. That rate is controlled by this exponent here. So if you make it a little bit closer to 1, then the growth is kind of slow. If you make it larger than 1, then the growth will be very, very large. And then when it comes around curvatures like this region here and this region here, you will have high stresses in these high curvature regions. Then you want to have a little bit more resolution in these areas. So the control for the resolution in curvatures or in narrow sections, like this section here, for example, are controlled by these two numbers. So if the lower the numbers, the more resolution you're going to have. So I'm going to make this 0.4, for example, or 0.3, and then this is 0.3 also, and then I build all again. Then it will take a little time to actually rebuild the mesh and give me a different distribution for the mesh that is not what they suggested originally, but I use actually my understanding of the physics and produce a mesh, an entirely different mesh, as you can see that in this situation here. So this is basically what we have, like a model that has also now a little bit more resolution, and we finish with the mesh. Then we can go to the study, and then we are ready to do the computation. And you can just click compute. So what it's going to do now is it's going to start evaluating the matrices that are required to solve the finite element equations in all of these domains. So already you can see here in the messages, so I'm going to just bring it up a little bit, and the number of degrees of freedom solved for in this particular model is not very large. It's only like 83,000 degrees of freedom, but it's sufficient for the model that we have, and we have more control over the mesh distributions, as we can see. So the results, we would be able to trust it a little bit more. And the process of the solution for the equations of the finite element is controlled by the solver. And I'm going to give a little bit of information on that solver. So what you'll see here is that I get a solution here. I get the stress distribution, and the distribution, the stress is the von Mises stress. So obviously the numbers are so large here, 10 to the 14, which means that I might have done something incorrect in the units. So if I probably put here the parameters just to check on F, we have under 50 MPa, which explains why I have such huge stresses that are very unrealistic. So I have to change the MPa to Newton, because the units of force is Newton, which is, so I can show you I got a mistake here. And then I go back to the study, and then I recompute the solution. So it's going to go back again and redo the solutions for me with the total system of elements. Note here that the incorrect results, I got 10 to the 14 numbers, which are quite unrealistic. And that's why I have to go back and check on my input data, and I found right away that the problem was in the applied force. Applied force was off by many orders of magnitude, 6 orders of magnitude. So while it's doing the computation, just a word on the finite element procedure. What it does is that it has broken the entire volume into pyramids. We call it tetrahedra. So each pyramid is like this, and it has inside here deformation, like the displacements inside. So what happens is that it does make the deformation. What it does is that it assumes a deformation field, as a displacement field in here inside the pyramid, either linear or quadratic. These are called shape functions, and based on that, it produces equations for the nodes of the pyramid. So this node here, and this node here, and this node here. These equations are the displacements for the nodes, the strain, and also the stress. And it does solve for the displacements essentially, and then after it solves for the displacements, then the code calculates the strains and the stresses. The way that it solves for the displacements is by a solver, and the solver is each point on the pyramid now, which is a node, has a displacement vector xyz, and it does assemble all of these into a huge matrix, and then it solves equations of motion by inversion of a matrix. And the inversion process, you can imagine if you have a very large matrix, it's either direct inversion, which means that solve everything at the same time, or indirect, which means that the matrix, it takes a little piece at a time and then it keeps doing iterations. So if we now look at the results that I have here is 10 to the 8. So it's a little bit better, but I think there must be something else here that is not unit-wise is not consistent. Oh, this is actually correct, because if you look at the results section, they are in units of Pascal. So let's just go back, and then we have, it usually produces a surface plot. This is a surface plot, and then you can choose what you plotting here. So the default expression that it plots is called the von Mises stress, and the Mises stress, M-I-S-E-S, is a variable that belongs to the function called solid. So the solid has actually, or an object called solid, and it has a function called Mises. You can replace this by any other output by introducing a replacement through you can plot either the forces, boundaries, you can plot the geometry, you can plot the mesh, or in our case here we want to plot things that relate to the results of solid mechanics. So the results that you can see here, you can plot the displacement, energy, geometry, load, and so on. So usually we plot the stress. So the stress, if you can see here, it has many different types of stress that can be plotted. The one that we use the most is the von Mises stress, which is here. And the von Mises, for example, if you click on this, then it actually it gives you von Mises GP, which is a different kind of von Mises at Gauss points, but I don't need that. Then I can go back to stress, and then I want to have von Mises solid. Like if I click on it, it shows here solid Mises. The next thing is the units. Then I choose the unit here to be MPa, just so that I can see it, because megapascal is a lot better. You divide this 10 to the 8 by a factor of 10 to the 6, and then you will have kind of a good range. So since I changed things here, then I don't have to rerun the model. All what I do is I'm changing in the plotting. So to replot, then you have an icon on the top left side of the model wizard panel, and you just click plot. Then it does go through everything here, and it plots it again in units of MPa. A lot of times the variation of the stresses are too coarse, like the elements are maybe very sharp variations. You can see that the maximum Mises stress is right here. This is where we expect it to be, because you have the force on the wrench and the side. The maximum moment is actually here, but this piece here is so strong, so it's not going to be having a high stress. But once you get into a lower cross-sectional area, then it's going to have to take up most of the stress. So to get a little bit better average result, because this is kind of more of a coarser result, then we use a function called polynomial preserving recovery algorithm, And this function kind of smooth out takes the average of different points. It's like a smoothing function in digital signal processing. So you take that, then it will smooth out the fluctuations and give you a better approximation. So instead of solid Mises, then you apply this function PPR of what? The argument is the solid Mises. So it will work on Mises, and it will actually filter it. And then when it filters it, then it just does like a recalculation. You can see now it gave us a different, smoother profile, and the maximum is 352 instead of 430. And this is much more reliable, this maximum. So we can actually design on that particular maximum. So I'm going to now stop at this point, and then in the next lecture, or the tutorial, I'm going to spend a little bit more time on an optimization of the design. In other words, how can we change some parameters in the design so that we can come back and optimize it and make it work better automatically. And this is the whole idea of parametric sweeps. So we define some parameters in the global, and we're going to take these parameters and then say I want to change it from initial value to final value in such and such a way, and then the program is going to run through many different cases of these parameters and give us the final results. And this will be extremely useful in the future for our studies. So let's just stop at this point, and then we will continue in the next tutorial.